Okay, in this section we're going to talk about how to find the equations of lines and planes in R3. Let's go back to R2 for a second and look at how to find the equation of this line that goes to this point and has this slope. We're going to do it a little different than what you learned in your pre-calculus class though. Let's look at it like this. See this point, negative 1, 4? Think of R0, instead of thinking of it as a point, think of it as the position vector being negative 1, 4, right? Every point can be thought of as, you can have a position vector with that as its terminal length, right? All right, so, and then instead of the slope being negative 2, you could think of the direction vector, 1, negative 2, would represent the slope. Every time x goes over 1, y goes down 2. So if xy is any other point on this line, remember this is a line with slope 2 that goes to the point negative 1, 4. If xy is any point on this line, it can actually be thought of as starting at the point negative 1, 4, and then moving parallel to this direction vector a certain length. So you can think of it like this. If xy has the position vector r, you could think of it as starting at this point and moving a certain distance along the parallel vector for the line, or the direction vector for the line. If you look at the components then of each of these and add them together, by looking at the components of that vector, you get the parametric equations for the line. And that might be a strange way to think about that, but if you apply that same idea to R3, that's how we're going to do it. So here we go. If you have to find the equation of a line in R3, the parametric equations, I should say, you need a point and you need to know the parallel vector or direction vector. Okay? Suppose we start at a point x0, y0, z0, and suppose our line has direction vector v. So here's v over here. R0 is the position vector for this point x0, y0, z0. If x, y, z is any other point on the line, and say r is the position vector for that point, you can think of r as being the sum of this position vector plus this vector here. This vector here would be some multiple of the direction vector, or the parallel vector v, right? So that's what this says. The way you can get from this point to this point is start at r0 and add a certain length, certain multiple of the parallel vector for the line. If you look at the components then, and then the x coordinates and y coordinates and so on, you get the parametric equations for the line. So you need a point and you need a direction vector. Once you have a point, the coordinates of the point go here, here, and here, and the components of the direction vector go here, here, and here. So how would you find the parametric equations for the line through these 2 points? You would first find the parallel vector, or the direction vector, by subtracting the coordinates. We get this. Then the parametric equations, remember x is equal to x0 plus at, which becomes negative 1 plus 4t. Y becomes 2 plus negative 4t. And z becomes 1 plus t. You could have used this point as well. The parametric equations would have looked a little bit different, but it turns out they would both be correct. Let's keep going. So remember, you need to know a point and a direction vector to get the parametric equations for a line. Here they want you to find the symmetric equations. We'll talk about that in just a second. Let's first find the parametric equations for the line through this point and is parallel to this line. Well, folks, if it's parallel to this line, couldn't we just borrow the parallel vector for that line, right? The parallel vector would become 1, 3, and 2, so you can go right to it. X becomes negative 2 plus 1t, y becomes 0 plus 3t, and z becomes 1 plus 2t. Now what's this business with symmetric equations? It's just a different way to write the line. If you solve each of these equations for t and set them equal to each other, you get this. And so this would be this symmetric equations. It's not a big deal, but it comes up on the homework. Determine whether these lines are parallel, intersecting, or skew. Skew just means they're not parallel and they don't intersect. That basically means these lines are lying in 2 separate planes, but that doesn't mean that the lines are necessarily parallel. All right, so how would you do it? Well, one way to tell if they're parallel is to look at the parallel vectors, or the direction vectors for each of these lines, and see if one of them is a multiple of the other. And it's pretty obvious they're not. You could also take the cross product, couldn't you, and see if the cross product is zero vector? But that doesn't mean they necessarily intersect. What you would then do to see if they intersect or not is you set the coordinates equal to each other. If you set the z coordinates equal to each other, you get this, and you can say s must be 1 minus t. I should mention something here. It's very important that these lines have different parameters, because they don't have to intersect at the same time. They just have to intersect at some point, right? So you should make sure you use different letters whenever you have two separate lines. Okay, so I have s equals 1 minus t. So then if you set the x coordinates equal to each other, wherever there's an s, you can replace it with 1 minus t, and you can solve the system of two equations and two unknowns. Don't get too excited yet. All we know is that there's a point on where the x and z coordinates are the same. Are the y coordinates the same at that point? And the answer is no, unfortunately. When you set the y coordinates equal to each other, you plug in you don't set them equal to each other. When you plug in 1/2 for t, you get that y is 1/2. And when you plug in 1/2 for s, you get that y is 0 on the other line. So the y coordinates don't agree, so the lines don't. There's no solution to the system of three equations, three unknowns, so the lines do not intersect. They're askew. All right, let's talk about a plane. That's kind of interesting. To a plane, you need to have a normal vector. That's a vector that's orthogonal or perpendicular to every vector in the plane. You also have to have a point. Point x naught, y naught, z naught. And the reason why that does it is because if x, y, z is any other point in the plane, you could form this vector v, right? You could form this vector v, and what has to happen is v cross n v dotted with n has to be 0. So that's exactly what we do. If x, y, z is any other point in the plane, you could form this vector v by taking the difference in the coordinates, dotting it with n, setting it equal to 0, and what you end up with is when you use the definition of dot product, you get this. When you multiply everything out, you can move all this constant over, minus ax0, minus by0, minus cz0, move it over to the other side and just call that thing d. So there's the equation of a plane that has normal vector abc and goes to the point x naught, y naught, z naught. So what do you need to find the equation of a plane? A point and a normal vector. So if you have a point that lies in the plane, and you know our plane is parallel to this plane, this should be an x, shouldn't it? Yeah. Then you could use the normal vector for this plane, because if two planes are parallel, their normal vectors, one will be a multiple of the other, so they'll both be orthogonal to the same plane. Okay? So what you do is, all you have to do is take the components of the normal vector that we're going to use and form the other vector. Remember how we do that? We go x minus negative 2, comma y minus 0, comma z minus 1, and you dot that and set it equal to 0. And when you do that, I get 2x minus y plus 2z is negative 2. How about this? See if you can do this one. Find the equation for the plane that goes through these 3 points. Hit the pause button and try this one. Okay, you need two vectors that you can cross, and the way you can form the two vectors, if you take this point minus this one, you can get one vector. And then if you take these coordinates minus the first coordinates, you get the second vector. So you got two vectors. Look at the cross product. I get I 3j plus 7k. Now remember, and you could use any of these points. You could have used this point, for example, and then if x, y, z is any other point on the plane, all you have to do now is form this vector x minus 2, comma y minus 1, z minus 0. Dot it with the normal vector we find, set it equal to 0, and I got 1 plus 3y plus 7z is 5. Let's keep on going. How about this one? Find the equation for the plane through this point and that contains this line. That's kind of interesting. You might want to draw a picture on some of these. It might help. Okay, so look. Think of it like this. You need to have a normal vector, correct? You have a point. Well, the way you can get a normal vector is to cross two vectors. One vector that would work would be this vector v. This vector v would be the direction vector, or the parallel vector for this line. Doesn't that lie in the plane? So that would be 1, negative 2, negative 1. But how am I going to get another vector in the plane? Well, you know you have a point on this line, 1, 0, 1. And you also have another point. Why not form a vector that goes that goes from this point to this point. If you go from this point to this point, this vector w, it turns out you get 3, 0, 0 when you take the difference in the coordinates. Then you can cross those two vectors. I'm going to cross v with w, and I get negative 3j plus 6k. So now that we have a normal vector and you have a point, I'm going to use the point negative 2, 0, 1. To form the equation of the line, all you have to do is let x, y, z be any other point on the plane, and remember the other vector is going to be x minus negative 2, y minus 0, and z minus 1. Dot product set it equal to 0. I get y minus 2z equals negative 2. Okay, these last two problems are a little bit harder, I think. Here are the equations of two planes, and the question is, are they parallel or do they intersect? And that's the only two possibilities for planes. So the question is, if they're parallel, then find the distance between them. If they intersect, find the line of intersection. Well, if you look at the normal vectors for these planes, you can see that one of them is clearly not a multiple of the other. That means they have to intersect. So how do you find it? Well, this is kind of strange a little bit. How do you find where two planes intersect? Well, believe it or not, you can just we're just going to push our way through. We're going to let y equal 0 and see if we can find x and z that would make that true. You could have picked other points, but if y is 0, you get x plus z is 4, x minus z is 2, so you get two equations, two unknowns. I picked y equals 0 because I knew this was easy to solve. And then so that means x is 3 when you add these together, and then z is 1. So look, there's probably there might be other points. Well, there probably aren't other points. But this is one point where there are other points. Yes, this is just one point on the line of intersection. There's infinitely many points, of course. So now that I know a point, I have to find the direction vector. The direction vector, if you think of it like this, where the planes intersect, this vector v, the parallel vector for the line of intersection, is going to be lying in both planes, so it has to be orthogonal to both of the normal vectors. So you may have to think about that for a minute, but if you take the cross product of the two normal vectors, that's going to serve as a parallel vector for your line. See? So once you have that, and you have the point 0, 3, 1, you could use parametric equations for that. Of course, your answer might look different if you had pushed through and got a different point than I did. Your parametric equations might look a little different, but they'd be right. All right, last one. Same situation, only in this case, I'm asking you the same question. Are these planes parallel or do they intersect? In this particular case, if you look at the normal vectors, you see that clearly this vector is negative 2 times this one. So this is a case where they are parallel. So now the question becomes, how do you find the distance between the two planes? And this is what you can do. If you can find a point on one plane and a point on the other, can't you form this vector v? Now, all you have to do then, the distance is just and if n1 is the, you can use either one, it turns out, but you could use the normal vector for one plane. If you look at the component, the absolute value, I should say, of the component of v on n1, then that would be d. The absolute value of the component of v on n1 would be d. So in that case, what that means is it's v dotted with the unit vector in the direction of n1. So the hard part is, how do you find a point on a plane? Well, it's easier than you think. I just let x be 4, y and z be 0, right? 4, 0, 0. And the other one, I said, well, okay, what if x is negative 3 and y is 0? So there's other points you could have picked, but those certainly work. So remember, I'm forming this vector v from one plane to the other. So the vector v, if you take the difference in the x, y, and z coordinates, I get negative 7, 0, 0. I'm going to use the normal vector for the first plane. So the unit vector in the direction of n would be, you take the components and you divide by the magnitude of n, which is 6, a square root of 6. So the distance is then the absolute value of the dot product between the vector v and the unit vector in the direction of n, n1. And so when you look at the dot product, you get 7 over square root of 6. Amazing, isn't it? All right, we'll see you next time. Bye-bye.